So now let's move away from first order differential equations as we move on to second order differential equations. So given the differential equation of the form p of x times the square y over the x square plus q of x times dy dx plus r of x times y equals g of x, where p, q, r, and then g are continuous functions of x, is said to be a second order linear differential equation. Now, second order simply because the highest order of the differential equation is 2, and then linear because the functions p, q, r, and then g are all functions of x. Now, if the right hand side of this differential equation is equal to 0, then we say that we have a second order linear homogeneous differential equation. So let's say if g of x is equal to 0, then we have a second order linear homogeneous differential equation. And then if g of x is not equal to 0, then we have a second order linear non-homogeneous differential equation. Now, our interest here is to focus on the second order linear homogeneous differential equation and how to obtain the general or the particular solution of such differential equations. Now, for a second order linear homogeneous differential equation, which is given as p of x times the square y over the x square plus q of x times dy dx plus r of x times y equals 0. Now we can represent this differential equation in prime notation. That is, we have p of x times y prime prime plus q of x times y prime plus r of x times y equals 0. Now, considering that p, q, and then r are all constant functions, or better still, they are constants, then we can represent the differential equation by replacing p of x with a, q of x with b, and then r of x with c. Mind you, a, b, c are all constants. So we are going to have a times y prime prime plus b times y prime plus c times y equals 0. Now let's consider a trial solution. Let's assume that we are going to assume that the function y equals e to the power m times x is a solution to the differential equation. So is a solution to the above differential equation. Now, if you make this assumption, then what this primarily means is that you are going to find y prime and then y prime prime from this function and then substitute that into the differential equation. So from this, we can obtain y prime by differentiating this function. Now we differentiate the exponent with respect to x, and then we have m. So the m appears here in front of the function, and then we are going to repeat whatever you have here. So that becomes times e to the power mx, and then if you want to find y prime prime, basically you are going to differentiate this. So you differentiate mx with respect to x, and then you realize that you have m, so you multiply m by m, and thus you have m squared times e to the power, we are going to repeat whatever you had, so e to the power mx. So this is y prime and this is y prime prime. The next thing we are going to do is to substitute these two into the original differential equation given, so that you are going to have a times y prime prime, that is m square times e to the power mx plus b times y prime, which is m times e to the power mx plus c times y, which is e to the power mx equals 0. Now at this point you realize that e to the power mx is common to each of the three terms, so we can factor that out so that we have e to the power mx on the outside. Inside of the bracket we have m square times e to the power mx divided by e to the power mx. This cancels out this, we are left with a m square. So you have a m square plus, now this cancels out this, we are left with bm plus, this cancels out this, we are left with only c, and this is equal to 0. So we divide through by e to the power mx, e to the power mx, and then we are going to have am square plus bm plus c equals 0. Now we call this the characteristic equation or the auxiliary equation of the differential equation. So this is the characteristic equation, or better still, the auxiliary equation of the differential equation. Now you realize that this is a quadratic equation, and hence the next thing we need to do is to obtain the roots of this quadratic equation, or better still, this auxiliary equation. Now we can do this either considering the method of factorization, or better still, using the quadratic formula. So assuming you are using the quadratic formula, then you can find the roots of the auxiliary equation to be equal to, you have negative b plus or minus the square root of b square minus 4ac, all divided by 2a. So plus gives you one root, and then minus also gives you the other root. Now depending on the nature of the roots of the auxiliary equation, three possibilities may occur, and we need to familiarize ourselves with these possibilities. So we are going to consider three cases here which depend on the nature of the roots of the auxiliary equation. So if the roots are, so we consider case 1. If the roots are real and unequal, if they are real and unequal, or better still, distinct, then we have m to be equal to m1, and we have m to be equal to m2, so that m1 is not equal to m2. Now if m1 is not equal to m2, then the solution to the differential equation is given by y equals c1 times e to the power m1 times x plus c2 times e to the power m2 times x. Now for case 2, that is if the roots are real and equal. So this time if the roots are real and equal, then it means that m is equal to m1, and that is the same as m2. Now if we denote m1 with the double root, then we have the general solution given as c1 times e to the power m1x plus c2 times x times e to the power m1x. Again, if m2 is used to denote the double root, then instead of m1 you are going to have m2. Now literally the value of m1 is equal to m2, so it doesn't really matter. Now let's move on to case 3. So for case 3, if the roots are not real, if this time the roots are not real, or we say that they are complex. If the roots are complex, then that is where you have m to be equal to alpha plus or minus I times beta. So with this, you can have m1 to be equal to alpha plus I beta, and then m2 to be alpha minus I beta. Now with this, the general solution is given by y equals e to the power alpha x times, into brackets we have c1 cos beta x plus c2 sine beta x. Now the values of c1 and c2 for all three cases can be obtained if we are given the initial conditions, or better still, the boundary conditions. Now in the next section, what we are going to do is to consider some examples covering all these three cases. So let's start by taking the examples one after the other. So now let's start off with example 1. So in this example, we are going to solve the differential equation y prime prime plus 3y prime plus 2y equals 0. So let's try to solve this together. So we have the differential equation y prime prime plus 3y prime plus 2y equals 0. Now to solve this differential equation, because we are dealing with second order linear homogeneous differential equation where the coefficients are constants, we can derive the auxiliary equation straight away from this differential equation. Now to do so, we are going to replace y prime prime with m squared, y prime with m, and then y with 1. So you are going to have the auxiliary equation, or the characteristic equation, to be m squared plus 3m plus 2 equals 0. Now the next thing is to find the roots of this auxiliary equation. So we multiply the coefficient of m squared, which is 1, by the coefficient of the constant, which is 2. So 1 times 2 is 2. Now we need to obtain two numbers that when you multiply, you get 2, and then when you add, you get 3. That is simply 1 and 2. So 1 times 2 is 2, 1 plus 2 is 3. So we have the factors to be m plus 1, and then we have m plus 2. So that is equal to 0. So first we have m plus 1 equals 0. We have m equals -1. And then next we have m plus 2 equals 0. And then we have m equals -2. So we can call this m1, and then we call this m2. Now since the roots are real and unequal, then we say that the general solution is given by y equals c1 times e to the power m1x. So we have -1 times x, which is -x, plus c2 e to the power m2x. So that is -2x. So this happens to be the general solution to this differential equation. So now let's move on to the next example. That is example 2. In this example, we are asked to solve the initial value problem y prime prime plus y prime minus 6y equals 0. We have y of 0 equals 1 and y prime of 0 equals 0. So let's solve this. So we have the differential equation y prime prime plus y prime minus 6y equals 0. Here also we can obtain or derive the auxiliary equation straight away. So here this becomes m squared plus m minus 6 equals 0. So we multiply the coefficients of m squared, which is 1, by -6, and then we have -6. We want to find two numbers that when you multiply, you have -6, and then when you add, you have 1. So first we have, let's say we have 1, 6. We have, let's say, 2 and then 3. So we can make this -2 and then plus 3. So when you multiply these two numbers, you have -6. When you add them, you have 1. So we are going to use -2 and then 3. So we have the factors to be m minus 2 plus 3 equals 0. So first we have m minus 2 equals 0, m is equal to 2, and then m plus 3 equals 0, m is equal to negative 3. So let this be m2, we have this to be m1. Therefore, since the roots are unequal, they are real and unequal, then we have y to be equal to c1 e to the power 2x plus c2 e to the power negative 3x. So this is the general solution of the differential equation. Now we are given the initial value conditions, and we need to solve further to obtain the particular solution of this differential equation. So what we are going to do is, here we have y of 0 equals 1. So we say for y of 0 equals 1, what this primarily means is that we have the value of x to be 0, and then we have the value of y to be 1. So we are going to plug x equals 0, y equals 1 into the general solution, because this is y and then we have values of x here. So that becomes, we have 1 equals c1 times e to the power 2 times 0 plus c2 e to the power negative 3 times 0. So this becomes 1 equals, now 2 times 0 is 0, and then e to the power 0 is 1. Any non-zero number raised to the power 0 is equal to 1. So we have 1 times c1, which is c1. The same happens to this term, so we are going to have plus c2. So we call this equation 1. So the next thing is for y prime of 0 equals 0, we have x to be equal to 0, we have y prime also to be equal to 0. So we are going to plug in, first of all we are going to find y prime, and then we plug in x equals 0, and then y prime also equals 0. So we are trying to find the first derivative of this general solution, so that becomes y prime equals, we are going to differentiate this with respect to x, so we have 2, so it becomes 2c1 times e to the power 2x, and then this becomes negative 3 times c2 e to the power negative 3x. So we have y prime equals 0. So on the left hand side we have 0 equals, now 2 times 0 is 0, e to the power 0 is 1, so that becomes 2 times c1 minus 3 times c2. So we can transpose negative 3c2 to the left hand side, so that we have 3c2 equals 2c1. We divide through by 3, and then we have c2 to be equal to 2 over 3 times c1. So the next thing is we are going to plug in c2 into equation 1. So we put c2 in equation 1. So for equation 1 we are going to have 1 equals c1 plus c2, we have 2 over 3 c1. So we want to find the LCM. So LCM between 1 and 3 is 3. 3 divided by 1 is 3. 3 times c1 is 3c1 plus 3 divided by 3 is 1. 1 times 2 is 2. So we have 2c1, and that is equal to 1. So we cross multiply, and then we have 3 on the left hand side equals 3c1 plus 2c1, and that is equal to 5c1. We divide through by 5, and you realize that we have c1 to be equal to 3 over 5. So this is the value of c1. And then for c2 is equal to 2 over 3 c1. So 2 over 3 times 3 over 5. This cancels out this. we are left with C2 to be equal to 2 over 5. So this is the value of C2. Now we can write the particular solution. That is, from this we have y equals C1, which is 3 over 5 times e to the power 2x, plus C2, which is 2 over 5 times e to the power negative 3x. So this happens to be the particular solution of this differential equation given the initial conditions. Now let's move on to the third example. So in the third example, we are going to solve the differential equation y prime prime plus 2y prime plus y equals 0. So we have y prime prime plus 2y prime plus y equals 0. So this becomes m squared plus 2m plus 1 equals 0. We multiply 1 by 1, so that is 1. We want to find two numbers that when you multiply you have 1, when you add you have 2. So that is basically 1 and then 1. So we have the factors to be m plus 1, m plus 1, that is equal to 0. So this becomes m plus 1 equals 0, m is equal to negative 1, and then m plus 1 is equal to 0. We have m equals negative 1. So here we have m1, we have this to be m1, we have this to be m2, and you realize that m1 is equal to m2, and that is equal to negative 1. So here you realize that the roots are real and they are equal. They are equal roots, real and equal roots. So the general solution is given by y equals c1 times e to the power negative x plus c2 times x times e to the power negative x. This is the general solution to this differential equation. Now let's move on to the last example, where we are going to solve the differential equation y prime prime minus 6y prime plus 10y equals 0. Let's solve this together as well. So you have y prime prime minus 6y prime plus 10y equals 0. So this becomes m squared minus 6m plus 10, and this is equal to 0. You multiply the coefficient of m squared by the coefficient of the constants, so 1 times 10 is 10, and then you want to find two numbers that when you multiply you are going to obtain 10, and then when you add you have negative 6. So let's say we have factors of 10. We have 1, 10, we have 2, 5. Now out of these two sets of numbers, there is no way you can add any to obtain negative 6. Okay, so straight away let's try to use the method, or let's try to use the quadratic formula. So we are going to use the quadratic formula, which is given by, we have m to be equal to negative b plus or minus the square root of b squared minus 4ac, or divided by 2a. Now we have a to be 1, coefficient of m squared 1, we have b to be negative 6, we have c to be 10. So let's plug in the values a, b, c. So we have m to be equal to negative 6 plus or minus, we have the square root of negative 6 squared minus 4, we have a to be 1, we have c to be 10, or divided by 2a. So this becomes 6 plus or minus square root of negative 6 squared is 36, negative 4 times 1, negative 4 times 10, negative 40, or divided by 2. So this becomes 6 plus or minus square root of negative 4, or divided by 2, and then we can express this as square root of negative 1 times square root of 4, or divided by 2. So here we can express this as 6 plus or minus square root of negative 1 is I, the complex number or the imaginary value I, and then square root of 4 is 2, all divided by 2. So we can simply express this as 6 divided by 2 is 3, so 3 plus or minus 2 divided by 2 is 1, so 3 plus or minus I. This is the value of m. This is the value of m. So we have m to be equal to 3 plus or minus I, which is equal to alpha plus I beta. So what this primarily means is that we have alpha, this is plus or minus, so we have alpha to be 3 and then we have beta to be 1. Now since we have a complex root, then the general solution is given by y equals e to the power alpha x into bracket c1 cos beta x plus c2 sine beta x. So basically let's plug in the values of alpha and beta. We have e to the power alpha is 3, so 3x into bracket c1 cos beta x, beta is 1, so 1 times x is x, plus c2 sine x. So this is the general solution to the differential equation.